Good morning, students. So in the previous modules we have been working with the individual system. This is the individual system representation. It consists of the input, output, and within the block, that is the transfer function. This is the individual system representation. However, if we have the system which is more complicated, it consists of more than one individual system, then it is the complicated system. It consists of more than one individual subsystems as shown here. So for these multiple systems, we want the response of a single transfer function. So what we want to convert this complicated system, which consists of the multiple individual systems, into a one system having one input and having one output and the transfer function in this block. So we want to convert this complicated system into this type of system having the input, output and this transfer function, and we want the response of a single transfer function. Now the multiple systems can be represented in two ways. There are two ways in which the multiple systems can be represented. One is the block diagram and second is the signal flow graph. Although neither representation is limited to a particular analysis and the design technique, however, generally this block diagram is used for the frequency domain analysis and design, and the signal flow graph is actually used for the state space analysis. However, neither of the representation is limited to a particular analysis and design as said earlier. Also, the block diagram algebra will be used to reduce the block diagram. That is, we want this complicated system into one transfer function input and output. So for that, the block diagram algebra will be used to reduce that. And in the signal flow graph, Mason rule is used to reduce the complicated system. Now in case of block diagram, we will have this input, output and the transfer function. However, the transfer function in case of the signal flow graph is represented by a line and signals are actually represented by the nodes. One more point is that the signal flow graph are advantages, that is, there is advantage of the signal flow graph over the block diagram, that they can be drawn more quickly and they are more compact as compared to this block diagram representation. Now in this we will discuss about how first we will discuss about this block diagram representation and then signal flow graph, and we will see that how to reduce these to get the transfer function. As you already know that the subsystem is represented as a block with input, output and the transfer function. Now as we already know, the subsystem is represented as a block with input and the output. This is the subsystem having the input, output and the transfer function. Now let us suppose that it consists of multiple subsystems. It consists of multiple subsystems as shown here. This is actually the space shuttle which consists of the multiple subsystems. There are many subsystems in this space shuttle. Okay, and so when the multiple systems are interconnected, a few more schematic elements must be added to the block diagram. So when we have large number of subsystems, then some new elements must be added to that schematic. These new elements are the summing junctions and the pick-off points. That is, these are the summing junctions and the pick-off points as shown here. When your subsystem is like that, it will have the multiple subsystems, and we have to connect that. For that we have the summing junction and the pick-off points. Now here the components of the block diagram for the linear time invariant system are shown here. In this case, the characteristic of the summing junction is that the output signal is the algebraic sum of all the three input signals. Okay, that is, output Cs is equals to R1s plus R2s minus R3s. Minus is because here we have the negative, here it is positive, and here it is positive. However, we have three signals, many number of the signals would be there, and we get the output like that only. That is, Cs is the sum of all the signals that are at this summing junction. Now the pick-off point, it actually distributes the input signal, that is Rs, undiminished to several outputs. So it gives the input signal undiminished to any number of the outputs. Now we will examine some of the common topologies for the interconnecting subsystems and derive a single transfer function representation for each of them. These common topologies will form the basis for reducing the more complicated systems into a simple system having a input, output and transfer function. Now first one is the cascade form. In the cascade form, we will see that intermediate signal values are shown at the output of the each signal, each subsystem. Each signal is actually derived from the product of the input times the transfer function. That is, if you see that the transfer function of this is equals to x2 by r, x2s by r2 rs is equals to g1s. So to calculate the this signal x2s, that is, to calculate the x2s, x2s is equals to, that is, transfer function times that input signal rs, and this is also for this second one, and this is also for the third one. So it is, each signal is derived from the product of the input times the transfer function, and the equivalent transfer function is shown here, that is multiplication of all these. So in this case you will see that the output Laplace transform divided by the input Laplace transform is equal to the multiplication of all the three transfer function, that is Laplace transforms. And also one more point, that this equation is derived under the assumption that the interconnected subsystem, that is, these interconnected subsystems do not load the adjacent subsystem, that is, this system does not load this adjacent subsystem. It means that the output remains same whether or not the subsequent this subsystem is connected. That is, output is independent of subsequent subsystems. Okay, it's a very important point. So if there is a change in the output, the subsequent subsystem loads the previous subsystem, and the equivalent transfer function is not the product of individual transfer function. Now this loading concept can be explained by this example. Let us suppose that we have a system that we have discussed also previously, and the transfer function of the system is V1 divided by Vi. We have a second system, and in the second system the transfer function is V2 divided by Vi, which is given by this equation. Now let us suppose that we connect this system, these two systems. We connect these two systems as shown here, and its transfer function is given by this V2 divided by Vi. Now the transfer function of G and G1 is given by this equation, which we have also discussed previously. Transfer function of G2s of this is given by this, and finally the transfer function of, and when we connect these two in this figure C, we connect these two circuits. Finally the transfer function would be the multiplication of two transfer functions, that is G1 into G2, which is given by this equation. Now this is a case that when we are considering that the transfer function is the we have the two transfer functions, and total transfer function is the multiplication of these two transfer function, so we get this one. However, when the network is placed in a cascade and we use the loop or the node equation, then the transfer function would be this one. This is the transfer function while multiplying both these transfer functions G1 and G2, and this is the transfer function which can be obtained by the loop or the node equations, and we can say that these both are not same. That is V2 divided by Vi, that is V2 divided by Vi in S domain is not equal to G1s into G2s. Okay. So it means that in this equation we have one more term for the coefficient of S in the denominator. It means that the system that we have connected is loading this previous system, and as a result it is the transfer function is not equal to G1 into G2s. So one way to prevent this loading is to use an amplifier between the two networks as shown here. It is, we use the amplifier between the two networks. This amplifier has high impedance input, so it has the high impedance input. Okay, input impedance is high, so that it does not load the previous network. It does not load the previous network. At the same time, that is input impedance is high. At the same time, it has the low output impedance, so that it has the low output impedance, so that it looks like a pure voltage source to the subsequent network. To the subsequent network, it looks like the pure voltage source. So with the amplifier included, the equivalent transfer function will be the product of the transfer function into amplifier gain K. That is, it is equal to the product of the transfer function into the amplifier gain K as shown here, and amplifier gain, gain K has low input, low impedance output, and high impedance input. Now second is the parallel form. In the parallel form, let us suppose that we have functions in which we have the input and output, same input and same output, that is we have the parallel subsystems. The parallel subsystems have the common input and an output formed by the algebraic sum of the outputs from all the subsystems, and the equivalent transfer function is the output transform divided by the input transform. Okay, so if we have the signal like that, we have the systems like that, that is three systems, so finally having same input and output is algebraically added, then finally it can be represented by a single block having the input and output as given by this block. Now the third topology is the feedback form. Now we have seen this repeatedly in the subsequent chapters also. The feedback system forms the basis of our study of the control system. We defined the open loop control system and the closed loop control system and feedback control system. A typical feedback system is represented by this, having the input transducer, then we have the controller, then we have the plant, then the output and the output transducer, and then the feedback. Okay, and this one is the simplified model. What we want to do, we want to convert this type of typical feedback system into the this simplest one, that is the simplified model. Now in the simplified model, you will see from the simplified model we see that this actuating signal ES is the sum of this signal, input signal, and this one, output signal, that is feedback signal. So this actuating signal is the sum of the RS shown here and the feedback signal. The feedback signal is, we have taken the feedback from that CS and into HS. Okay, in this case the input is CS and output is this signal, so CS into HS depending upon whether it is positive or negative. Okay, now we also know that CS divided by ES, this CS divided by ES is equals to the transfer function GS, so CS is equals to ES into GS and ES is given by CS by GS. Now substitute this into this equation, we get, substitute this into equation. Also you will see from this we have negative and positive, so here we have to correct it, we have to use as R as minus plus GS minus plus CS HS, that is, since it is minus plus, summing point is minus plus, if it is plus minus then this would be plus minus. Now substituting this into this equation, finally we are getting the transfer function CS divided by RS as GS divided by 1 plus GS HS. So the transfer function CS by RS, that is output by input RS, is given by GS divided by 1 plus minus GS HS. It means that if this is negative, this signal is first negative, then it is positive. It means that if the signal is negative, in this case if the signal is ES is equals to RS minus CSHS, then the transfer function would be GS divided by 1 plus GSHS, and if it is positive, it is added, feedback signal is added, then it is negative here. So this is the feedback form. Now this is also called the closed loop transfer function. This is called the closed loop transfer function because you can say that loop is closed. And other is the open loop transfer function, and open loop transfer function can be simply represented by GS into H, as this is the open loop transfer function and this is the closed loop transfer function. Now we have explored the three different configurations for the multiple subsystems. For each we found the equivalent transfer function. Since these three forms are combined into complex arrangement in physical system, recognizing these three topologies is the prerequisite for obtaining the equivalent transfer function of the complex system. Now we discuss that how these systems can be, complex systems can be made into simple system. Now before we discuss about this reduction of the block diagram, it must be, we will discuss about the moving blocks to create the familiar forms. Now it is not always that the familiar forms are not always apparent in the block diagram. For example, we will see that, let us suppose that we have a system in which we have the summing point, and after that summing point we have here pick-off point. So it would not be possible to get, if there is the pick-off point at that very particular point, then it is not possible to use that to obtain the transfer function, because the pickup point is there here after that summing point. So it means that the signal will disappear if we convert this into one transfer function. So we have to create the familiar form so that we can easily by using this block diagram algebra, we can easily convert all it into single input and output in one transfer function. So here we have to create the familiar forms. Now let us take a small case. Now let us take a simple case in which we want to move the transfer function. We want to move the transfer function to left or right of the summing junction. That is, this is the transfer function GS. We want to move to the left or to the right of this summing junction. Here we want to move GS after this point RS. That is, after RS we want to move GS to this point. Then we will see that this signal SX, it also has GS in its loop. It means that it is also multiplied by the GS. It means that when we moved that GS to this point after RS, it means that this XS must be multiplied by the GS so that signal doesn't break, it must have the same signal. So we multiply SX with GS, so similar form can be obtained. That is, RS, previously RS was and XS were multiplied by GS. Now we have taken GS before RS as shown here, and since XS is also multiplied by GS, so we also place a block GS so that this signal CS remains the same. Similar is the case in this. If we want to take the GS after the summing point, let us suppose that we want to take the GS after this summing point. Here we want to take the GS. Now since RS is multiplied by GS, however XS is not multiplied with GS. And if we place this GS here, then XS is also multiplied by the GS, and as a result signal CS is not as the previous signal. So what we do, we place one more block near XS, so that this is 1 by GS, the transfer function of that is 1 by GS, so that when this is multiplied by this GS, so it will nullify and we are getting 1 only. And as a result, whatever signal is there in the previous case also, we get the same as here CS. So we get the familiar form. So in this case, what we have done, we have taken this transfer function before the summing point and then transfer function to the after the summing point, and we can see that how this can be done. Now let us take the case of the pick of points. Now equivalent form of moving a block. To the left past a pick of point and to the right past a pick of point. So this is the pick of point and we want to move this block to this. Here we will see that here whatever the signal is going is RS, here the signal is going is RS. So if we put the block GS here, then whole of the RS is multiplied by the GS and we are not getting output as RS. However, to make output as RS, we put one block here, that is 1 by GS, so that GS into 1 by GS is nullified and we are getting RS only. Similar is the case with this also. Okay. Now in the second case, what we have done, we want to take this GS to this. Okay. Simply RS is multiplied by the GS initially. So in all the blocks, this RS is multiplied by the GS. So in this way the output forms are created so that the output signal remains the same. It remains identical whatever be the we have done, that is whatever be the arrangement of these pick-up points and this summing points we have done, but the output signal must remain same in this case. Now let us take one example. Now let us consider a block diagram. We want to convert it into a single transfer function. Now you will see that here we have the 3 summing points and then we have a pick-off point also, and we have 2 forward path transfer function, that is G2, G3 and then feedback H1, H2 and H3. One way to do it, first we take this feedback, we solve it, and second we take this and solve for the transfer function, and we take this and solve for the transfer function. So one way to do that. Second way, that as we have discussed in the this previous that is some time back about the familiar forms. So we have H1, H2 and H3. So since they are connected to one summing point, so we take the sum of all 3 and connect together, since as we have done in the as we have discussed, like this one, that is structure is similar, that is output is at the summing point and we can sum all the 3 things. So we can use same here also, that is we sum all the 3. Since we have negative, positive and negative, so we have used here positive, negative and positive because the summer that we have used is negative. If we have used here plus sign, then it would be minus, plus and minus. Since we have used negative sign, so it is this positive, negative and positive. So finally G2 into G3 equals to G2 into G3 into G2, and this total what we are getting is H1s minus H2s plus H3s. Now this is a feedback form. So what we do, we calculate the transfer function of this feedback form. As you already know, the transfer function of this feedback form is given by, that is, gs divided by 1 plus gshs if this is negative. Okay, so same we can use here also. So we can use same here, that is gs means that g3 g2 divided by 1 plus g3 g2 into h1s minus h2s plus h3s. Now same is used here, and after that we find the transfer function of this feedback form. We multiply it with g1s, because whatever we are getting is this one, that is g1s, and let us suppose the transfer function of the feedback form is, let us suppose that gfs, so this is cs, and these two are multiplied, and finally we are getting this transfer function, that is g3s into g2s into g1s divided by 1 plus g3 g2 into h1s minus h2s plus h3s. Now let us take one example. We reduce the system which is shown here into single transfer function. So here what we do, we have to reduce this system into the single transfer function. Now from this we will see that there are different ways to do that. It depends upon the thinking of every individual who is doing that. So here we can say that here in this case, this seems to be the feedback form. So we can calculate the transfer function of this feedback form. We can bifurcate this summing junction into two junctions, because it has we can do that. So these summing junctions can be bifurcated into two, and we can get the feedback. We can get this transfer function of this feedback form. Let us suppose that transfer function of the feedback form is gf. After that we will see that this is also a we'll see that this is the pickup point, and if we take this pickup point here, then in that very case we are left with only these two signals which are in parallel, and we can add these two signals. And if we take this signal here, that is at this very particular point, it means that since this signal is not multiplied, V3 is not multiplied by G2, so if we take this signal here, then we have to multiply this signal with 1 divided by G2 as shown here. That is, this is the transfer function of the feedback system, and after that we take this point and then we multiply it with 1 by G2, so that before that it was here. So we take here and multiply it with 1 by G2, so that finally we are getting the G2 has no effect on the final signal, and finally this is the parallel form. So we have to add these two, and finally we are getting this feedback form, and we are getting this parallel form. Now there are the different ways to solve the left whatever is left. One is that we have this feedback and we solve it and then we multiply it. Second is that what we have done, we take this G1 near about to this G2. So we take this G1 to G2 here. Since H2 was not connected with this G1 here, so in this, when we take this G1 to G2, we divide H2 by G1. And finally we are getting this and this one, H1s, and this is the feedback form, and we convert this feedback form, and finally we are getting the last feedback form like that, this transfer function and this transfer function, and finally we are getting, this is also the feedback form, and we are getting the two transfer functions out of that, and finally multiplying this we get the transfer function of the whole of the system. So in this way we calculated the transfer function of the whole of the system. That is, we converted the first we convert this feedback form. After that we see that if we take this takeoff point to do this, then we can add these things. It is a parallel form. Then we have done that. After that we take this G1 to G2. There is other way to do also. We can solve this first and then after that this loop, but whatever is the thing, whatever is the understanding of any individual, he can do like that, and finally we are getting the this final transfer function. In this way, by using the block diagram algebra, you can simply do that. Now let us take another example which you have to do at your own end. Here we have this. Yes, we have this block diagram. Simply you can by using this block diagram reduction techniques, you can solve this also. Here we have this parallel form. We can convert the parallel form, and then we have after that we will have this feedback form, and after the feedback form finally we have the final feedback form, and then we multiply with this. Sorry, this is also included in the feedback form. So in this way you have to do at your own end, and the transfer function for this is equals to Ts is equals to s cube plus 1 and 2s4 plus s square plus 2s. So in this we have examined the equivalence of several block diagram configurations containing signal systems, summing junctions and pick-off points, and the configurations were the cascade, parallel and feedback forms. And during the block diagram reduction, we attempt to produce the easily recognized forms and then reduce the block diagram to a single transfer function. And now in the next section we will examine some of the application of this block diagram reduction. Thank you very much.